Hello, today we are starting a major unit on the mathematics of chemistry. We're going to break this unit into two parts. The first portion of this are simple calculations that you can easily solve based on these examples that I'll be showing you. The first lesson of this unit is how to calculate empirical formulas and formula mass. So for this first example question, this will lead you how to solve these problems, but in a very simple way. So the first question that's listed here, reduced to simplest form, you are given this molecular formula, C4H10. And if you remember from the organic unit, that is the molecular formula for butane. So to reduce this to its simplest form, we are just going to find the greatest common factor between the subscripts of the two elements in this formula, which would be 2, and we will divide it out to reduce this formula down to C2H5. The next questions, we're looking at the masses, which you can find on the periodic table, and you can round these off to the nearest whole number if you wish, or you could leave the full decimals since you are able to use a calculator for these problems. So the mass of 1 carbon is approximately 12. The mass of 4 carbons, therefore, would be approximately 48. The mass of 1 hydrogen is approximately 1, so therefore the mass of 10 hydrogens is approximately 10. Basically, we just answered the aim in this do now question in a very simple way, but I will walk you through definitions and how to solve some example problems on your own so you can be prepared to solve more of these in class with one another. So we've looked at different types of formulas in this class already. We've looked at structural formulas. That would give you the shapes of molecules. These would be the drawings. They'll show you the numbers of bonds between different elements and the overall shape the molecule would take on. Molecular formula would be the elements and the quantities, so just letters and numbers, no shapes at all. And now we're looking at empirical formula. So the definition of an empirical formula is that it's the lowest whole number ratio of elements in a compound. The way that you would find an empirical formula is by finding the greatest common factor between all elements in that formula. The example here that I give you is the formula for hydrogen peroxide. So hydrogen peroxide's molecular formula, the actual formula for hydrogen peroxide, is H2O2. The greatest common factor between both subscripts in that formula is 2, so we can factor that out. Therefore, the empirical formula of hydrogen peroxide is HO, a 1-to-1 ratio of hydrogen to oxygen. Now, again, that's not the actual formula for peroxide, it's just the simplest ratio we can make out of its elements. This next example, C4H8Br2, which is a halide, back to the organic material, so that's the molecular formula. And therefore, we can easily calculate its empirical formula by finding the greatest common factor between all of the subscripts. So 4, 8, and 2 have 2 as the greatest common factor. So the empirical formula would be C2H4Br. We can't take it any lower than that because now the bromine has a subscript of 1, and that's as far as we can go. The last example here then, what is the empirical formula for a compound with the molecular formula of P4O10? Take a second to think about it. And you should have come up with a greatest common factor of 2 between the numbers of 4 and 10. So the empirical formula is P2O5. Pretty simple stuff. Here are some more examples. So, if you'd like, pause this video and work these out on your own, and I'll come back in a few seconds. All right, so let's go through and solve these. In the first column, C8H18, the greatest common factor between 8 and 18 is just 2. So if I divide that out, my empirical formula would be C4H9. If you're ever not sure, and you take out a factor and it turns out that it could be reduced further, keep going until you get to the lowest ratio of the elements. The next one we already did on the prior page. Next one, again, we have subscripts of 2, so we could factor both of those out. The fourth one, 3, 6, and 3, each have a factor of 3 in common, so the empirical formula would be CH2O. So we have a 1 to 2 to 1 ratio of carbon to hydrogen to oxygen. And the last one in that first column, we can divide out a 2, so NaCO2. Second column. Now, water, that is a molecular formula. That's the actual formula for water. It also happens to already be in its lowest whole number ratio, so it's also empirical, which is possible. Another couple simple compounds that have the same molecular and empirical formulas would be ammonia, right? It's the actual formula for ammonia, as well as being in its lowest terms, and methane. Simplest terms, and the actual formula, or carbon dioxide. Next example in this column, we can divide 4 out of each of these numbers. So the lowest ratio would be 1 to 2 carbon to hydrogen. C7H12 already is in its empirical form, so this is both molecular and empirical as well. So it's the actual formula. It's the actual molecular formula for, organic hydrocarbon 7, so that's hept, fitting in with the alkyne formula, that's heptyne. It also happens to be empirical. This next one, from the organic chapter, you should recognize that this is a type of organic acid. When you solve for the empirical formula, you can combine the elements and add them all up and then figure out if it could be reduced. So for the carbons, there's 2 total carbons, there's 4 total hydrogens, and there's 2 total oxygens. So they can all be reduced by a factor of 2. So this, if I combined everything together in that order doesn't really matter if it's all jumbled up like this, just to get your numbers straight. And then the last one, C4H6, greatest common factor would be 2. So C2H3 would be the empirical formula. Very simple concept, just remember the definition. Don't overcomplicate it for yourself. Empirical means lowest whole number ratio. The next concept we're going to look at in this lesson is called formula mass, and it's just what it says. It's the mass of a formula. So you will find all the atomic masses on your periodic table. So use it. And you'll see this explained or listed in various ways. So you might see it listed as formula mass, you might see it listed as gram formula mass, you might see it listed as molecular mass or molar mass. It all means exactly the same thing. So don't get confused by the terminology. Depending on the context, they might use a different term to explain this, but it all means the exact same thing. It's the mass of a substance's formula. We'll talk about the units that would be derived from this later on in the chapter. So the easiest way to explain how to calculate formula mass, because this is not on your reference table T with your other calculations, is to work through an example. So here's a simple question. What is the formula mass of, this is potassium carbonate. I'm going to keep reviewing formula writing and naming with you. You need to know these skills. So what you can do to solve this in a very methodical way, you'll find that I'm very, very methodical in how to solve all of these calculations. To find the formula mass, you're going to list each of the elements. So we have to separate everything. So even though CO3 is a polyatomic ion of carbonate, we have to separate everything when we're calculating the formula mass. We can't keep it together like we could when we were balancing equations. Now we're just looking at masses of things. So the first thing, again, we're going to do is list out our elements. The next thing we're going to do is count them. So counting is very important, just like it was when we were balancing equations. So you need to make sure you count carefully. If you see parentheses, make sure you take those into consideration. In this case, there aren't any, but make sure you understand that subscripts refer back to the element that immediately precedes them. And if there is no subscript, it just means there's one. So I've listed them out: 2 potassiums, 1 carbon, and 3 oxygens. Then you're going to multiply those quantities by the atomic masses that you would find on your periodic table. And you can see here that I rounded these off to the nearest whole number. You'll see on your periodic table that most elements' atomic masses are very close to whole numbers. So remember your rounding rules. If it's above 0.5, you can round up to the nearest whole number. If it's lower, you'd have to round down. If you don't want to round, you don't have to, because you have the use of a calculator and you have your periodic table right in front of you. So you can just write down the entire mass. So anyways, you just write down the mass of the individual elements, you multiply across, so the quantity that you have times the mass of that element, you get your totals for your individuals, and then you just add them up. The unit for formula mass can be listed in different ways. If it just says formula mass, we would say that it's the unit would be atomic mass unit, or AMUs. But don't get too bogged down in the units at this point based on the questions. Just kind of get the numbers down for now. Here's another example. This is an actual Regents question. So this one brings in the use of parentheses to make sure that you're counting properly. And you'll see that even if you round your atomic masses off to whole numbers, or if you choose not to round them off to whole numbers, the answer choices that they give you span such a range of values that even if you round a little bit differently than whoever wrote the question, as long as you're counting properly and calculating properly, being off by a couple tenths or even by one whole number is going to make much of a difference. So I'll show you what I mean when we solve this problem. So again, we are going to list our elements following the example from the prior slide. So we have nitrogen, hydrogen, phosphorus, and oxygen. We separate it. Even though we have the ammonium ion and the phosphate ion, we have to separate everything. The next step is to count however many we have of each of those elements, and we have to distribute. We have parentheses around the polyatomic ion of ammonium. The 3 that is outside those parentheses gets distributed to both elements inside, including any subscripts that they may contain. So the total number for the nitrogen is 3, and the total number for the hydrogen is 12. For phosphorus, there is no subscript next to it. There's no parentheses around the phosphate, so I just have 1. And then we have 4 for the number of oxygens. Next step is to find your atomic masses, which are on your periodic table. So nitrogen's is approximately 14.3, which we can round off to 14, and that's okay. Hydrogen's about 1. Phosphorus is approximately 34, and oxygen is 16. As you do more and more of these, you're going to end up remembering a lot of these atomic masses, but please don't rely on your memory when it comes to answering questions like these on tests. Use the periodic table. Use the information you have available to you, because you don't want to make silly mistakes. It happens all the time. Okay, so then we just multiply across. So 3 times 14 is 42. 12 times 1 is 12, 1 times 34, and 4 times 16. We add up our values, so 4, that's 12, 9, 6, 1, 52. So even though I added a little bit differently, and I think I might have put phosphorus wrong, but because I'm not using my periodic table. Anyways, my answer here of 152 is obviously way closer to 149 than any of the other answer choices. So whoever wants to correct me in class about my mass of phosphorus, 5 points to Gryffindor for you. All right, next example here. I'm going to go over these 2 examples with you, and then the last 2 I'll leave you to solve on your own to bring to class. Okay, so we have calcium chloride here, very easy example, no parentheses involved, so we're going to list our elements, we're going to count our elements, we're going to multiply by their masses. So calcium's mass is approximately 40, and chlorine's mass, This one always trips people up. It's like 35.45 or something. So you can round it off to 35, you can round it off to 35.5, but don't round it off to 36. Most cases, for Regents questions, for their answer key purposes, they'll round it off to 35. But again, if you choose to use the decimal numbers, those are fine too. Multiply across, and we get approximately 110. For constructed response questions, because I'm giving you the flexibility of rounding, there will be a range, a small range of acceptable answers that I will take. So always make sure you show your work. So if when I make my answer key, I round it off, let's say I rounded off 35 to 35.5 and you kept it at 35, our answers would be a little bit different, but I'd still give you credit because I saw the work that you did and saw that you rounded off chlorine to the whole number. That's fine. And the second example here, this is ammonium hydroxide. So we'll separate everything out. So we have nitrogen, hydrogen, oxygen, and we have hydrogen again, but I'm not going to list it again because I can just combine it with the other ones. So I have one nitrogen. I have a total of 5 hydrogens, so be careful with compounds like this. And I have 1 oxygen. So I will multiply across by their masses. By now you might even be memorizing some of these simple ones you're seeing over and over again. Oops. And I will add up, so I will get approximately 35 for my mass. Easy stuff. The last 2 slides, I'm going to have you solve these on your own, including the work, and bring them to class so that we can compare our answers, discuss the method of problem solving, and then let you work on some examples with each other. So I hope this was helpful in showing you how to calculate the empirical formula of a compound from its molecular formula by reducing it, and also calculating the gram formula mass of a substance using a simple method that you can apply to any formula you're asked to solve this way.